So let me begin by briefly summarizing what we looked at last time. So in the first lecture, we briefly reviewed some basic aspects of cosmological correlation functions, and we looked at why we care about these objects in cosmology. In particular, we looked at what we currently know about two-point functions of primordial fluctuations. And we also looked at, in order to really learn more about detailed dynamics of inflation, about the primordial universe, it is somewhat necessary to go beyond these two-point functions or Gaussian statistics and really look at non-Gaussianities. So non-Gaussianities mean these higher point correlation functions beyond Gaussian two-point statistics. And the reason is that these higher point correlators contain a lot of information about the interactions and the particle content of the primordial universe. Okay. So far, we haven't actually measured these high point correlators yet, but a large program of observational cosmology in the next decade is going to be about trying to measure and constrain better these high point correlators. But even in the absence of any immediate discoveries of this non-Gaussianity, it is actually very useful to study these objects in order to really learn whether we can learn something deep about the very structure of quantum field theory in cosmological spacetimes. So we want to study these objects from a more theoretical perspective. And as promised, today we'll start to learn how to compute some of these objects. And I'm assuming that not many people have seen these calculations. So I'll try to be very pedagogical in today's lecture, and we'll try to get our hands dirty a little bit. Let me go through these calculations. Okay. So yesterday's lecture, everything was a little bit abstract and conceptual. But if we want to really get our hands dirty and then start calculating these objects, we have to, I need to give you a more precise definition of the actual observables that we want to compute. Okay, so let me start by defining the observables in cosmology. So unlike in particle physics, we don't really consider S matrices or scattering amplitudes in cosmology because they're not directly observable quantities in cosmology. So there's a difference between observables in particle physics and cosmology. So S matrix is defined as the overlap between in-state and out-state. But in cosmology, there's no, first of all, there's no well-defined out states to consider at late time during inflation because we are in a time-dependent background. Particles are continually created just due to the time dependence of the background. So there's no sort of well-defined out state we can consider on the boundary that we are evaluating these correlators at future time during inflation, and also. We don't get to prepare the initial state, unlike in particle physics. Okay, so we don't get to prepare in state. However, it turns out that there's a sort of a natural and distinguished in states we can choose in cosmology, and these are so-called Bunch-Davies or Hartle-Hawking state that are defined to be, they are denoted by this state, BD. Okay, and this is essentially the vacuum choice that is analogous vacuum choice as in Minkowski space. So the argument is the following. So I'm drawing this end of inflation surface in this 2D picture, and there's a horizon given by inverse Hubble scale. Now, yesterday we saw that when we look at these primordial fluctuations, they really start from this tiny quantum fluctuation, whose wavelength, physical wavelength, is much smaller than the Hubble scale, the horizon scale to begin with. And then as time goes up, these fluctuations eventually exit the horizon and then freezes out. But when we go to the far past, these fluctuations have a wavelength that are much smaller than the size of the horizon. So from the point of view of these little fluctuations, they effectively feel like the background is actually flat. They don't really feel the curvature they can feel when it goes late time. So at super early times, these fluctuations are effectively in the Minkowski background, and that is really just a statement of equivalence principle, right? The physical wavelength is much smaller than the size of the curvature, and therefore, there's a natural choice of the vacuum state that we can have in inflation, which is the so-called Bunch-Davies state. Okay. Okay. So the question is, how do we compute correlation functions in this given this Bunch-Davies state? So we want to do the following. We want to we have some say quantum operator O, and we want to evaluate the expectation value of this operator at some time t. Okay, and we will choose this time t to be some late time during inflation. Okay. And the way we do this is that we have this surface where this operator lives. We're going to start with the Bunch-Davies state in the far past. Okay? And then we're going to evolve this Bunch-Davies state to the future. And then we're going to take the overlap with another Bunch-Davies state to the left. And then we're going to sandwich this operator, this state with this operator. Okay. So if we write this out, then what we are computing is some sandwich between initial Bunch-Davies state with some operator O at time t and some time evolution operator. Okay. So there's and then we time evolve using this interaction Hamiltonian. With the time ordering operator here. And then for the Bunch-Davies state on the left, we again anti-time evolve this time, again with the interaction Hamiltonian. Then we do this time evolution from some time in the far past to the time t that we are evaluating this correlation functions. Okay, and because we are effectively taking this expectation value with this both of these being in states, this is the way this computation is done is using the so-called meaning formalism. Okay, there's another name for showing a Keldysh formalism. Okay, so this is basically the formula you can use to compute these correlation functions, and you can take this operator to be just a product of scalar fields if you want to compute some high-point correlation function. Okay, so that's one way of computing these correlation functions. But there's also a different way, slightly different way that utilizes so-called object so-called wave function of the universe that I'll also tell you about. Okay. You can also compute fermionic operators. Yeah. So typically, fermionic fields die off at late times during inflation. So they don't survive themselves when the inflation ends. So if you have like some coupling between the scalar field and the fermions, then fermions can indirectly contribute to the correlation functions through the scalar coupling. But you have to have scalar operators, massive scalar operators. These are zeta fluctuations because those are the fluctuations that actually survive and become frozen out during inflation. Okay. So let me tell you about this wave function approach. So the idea is basically using the idea from quantum mechanics. If you want to compute some expectation value, say product of this some scalar field, then we can compute it by doing this path integral with some probability distribution given by the wave function squared. Okay. There should be some overall normalization constant as well. And this wave function is really a wave function now that depends on this field. And this is defined to be the overlap between some particular field eigenstate that gives some configuration that looks like some configuration that has some particular field profile phi of x at some late time surface, and then with this initial state. Okay, so this is basically the probability of starting from this Bunch-Davies state, and then at late times we're having this particular field configuration on the late time slice. And this overlap can be expressed in path integral in the standard way. Okay. But we want to integrate over all field configuration with a particular boundary condition where this field reduces to the Bunch-Davies state in the far past, and then the field reproduces this exactly this spatial profile at late times. Okay, so when we do this path integral, we want to impose boundary conditions where this field that we are integrating over at super early times, it gives this Bunch-Davies state, and at late times, when t goes to some t star, okay, so this will be some t star, then it becomes this little phi of x. Okay. Now we can impose this condition. So also we want to really in the end compute the correlation function in the interaction vacuum. And typically we can use the standard trick where we can evolve with the I epsilon prescription, in which case this field should be exactly 0 when we slightly rotate the contour with a small I epsilon. So here, infinity minus, I'm defining to be infinity with a little I epsilon. Okay. So how do we compute this path integral? So we will be mostly interested in the tree level process for now. So in that case, we can approximate this with a saddle point approximation. Okay. So this will be dominated by the saddle point, which is given by just the action with a classical solution for this phi field. Okay. So this phi field is really also some function now that depends on this phi. Okay. Okay. So this is basically what we want to compute in order to get this wave function. And then once we have this wave function, we can plug it here in this path integral. Do this path integral to get the desired correlator in the end. Okay. So let me show you what you get in the end when you compute this wave function. Okay, so when you evaluate this action, evaluate with a classical solution, then in perturbation theory, there will be some expansion in this. There's if the interactions are small, there will be some order parameter with a coupling constant. Then there will be some powers of this phi field in the action. So in perturbation theory, what you can do is to expand this to higher order in this phi, and you can expand in this in this way. So so as you see, in perturbation theory, this is a general expression that we can write down for the wave function. This is the expression written down in position space, but we will typically be more interested in computing this in Fourier space. So this is the corresponding expression in Fourier space. So you see that at nth order, there's an n product of this phi field multiplying some coefficient that I'm denoting little psi n. Okay. And this little psi n has name. They're called the wave function coefficients. By the way, here's my Fourier convention. So this when I Fourier transform function of x, I have this 2 pi cubed in the integral measure. Okay, so let me also mention why we might even consider this way of computing correlation function instead of using the inning formalism. Okay, and the reason are following. So if you look at this expression, we see that we can kind of think of the wave function as being the square root of correlation function. So this is actually very similar to comparing the S matrix and the total cross section. Okay, so psi, the wave function, is in some sense more primitive. It's a more primitive object than the correlators themselves. Okay, so it's similar to S matrix versus the total cross section. And as a consequence, it turns out that the structure of psi is often simpler than the structure of the correlation functions. And by simpler, I mean that it has a nicer properties involving singularities and the implications of unitarity and so on. And also, the analytic structure is often much more easily interpretable for the wave function than the correlator. Okay, so this is some sort of an intermediate object that we are going to study in this lecture. Okay. Any questions about this so far? Yeah.
After the Solomon approximation, they use the information that we take quantitative with branches. So what happens if we take, for example, alpha?
Yeah, so you would impose a different initial condition in the past. Okay, so instead of having 0 with this I epsilon prescription, you would have something else. You might impose some cutoff or some linear combination of some solutions that you get. So it's a different boundary condition. Yeah. So actually, now what I'm planning to do is actually go through this calculation using the quantitative vacuum, and then I'll explain at which point you can impose different boundary condition for at this step. Any other questions? Okay. So let's now look at how this computation is done. And to do this, we will look at the simplest possible model we can ever consider, which is just massless phi field in flat space. Okay, so this object, the wave function, even though it's called the wave function of the universe, you can consider this object even in flat space. Okay, so here Okay, so even in Minkowski, you can try to compute some equal time correlation function at some particular time, and then compute the corresponding wave function. So that's what we'll try to do. And to make our life even simpler, we're going to just consider free theory to begin with. Okay, so the goal would be to really compute this object, two-point function, using this technique. Okay. All right. So to do that, we are basically evaluating this classical action. So let me first write down the action for free theory, okay, in Minkowski. Okay, it's extremely simple. Okay, so I have a minus sign here because I'm using mostly plus signature. Okay, so it should be capital psi, phi. Okay, now what we want to do is to solve the equation of motion for this phi field. Okay. So this equation of motion, and then we want to solve it in Fourier space. And in Fourier space, the equation just becomes the usual simple harmonic oscillator. Okay, so the solutions are the following. So we have a linear combination of two plane waves, one with a positive frequency and the other with a negative frequency. Okay. And then we will impose the boundary conditions that we had, two boundary conditions, in order to fix this coefficient. Okay. So first, let's look at this condition, the Bond-Davis initial condition. So we want to impose the condition that when we take t to minus infinity with the I epsilon prescription, then we want this solution to be 0. Okay. So if you want to do that, then we have to take only one of the solutions. So so that implies that C2 has to be 0. Okay. So if we impose this is 0, then this implies that C2 has to be 0. Okay. So that's this boundary condition. And then we want to impose the other boundary condition as well. So the second boundary condition is when we take t to t star. So here, let me take t star to be 0. Okay, so we are evaluating this wave function at t equals 0. Then we want this to be equal to this scalar profile phi, little phi. In Fourier space, it will be phi sub k. Okay. So when we set C2 to 0 and then take t to 0 for this boundary condition, we see that the exponent function just becomes 1. So that implies that C1 has to be phi of k.
So phi k is the value or?
Yeah, so you're assuming that there exists some particular spatial profile of phi at this t equals to 0 slice. And then in order to have that, so we are basically computing the wave function, giving that spatial profile. And then to get the correlation function, we will integrate over phi to get the correlation function. Okay. So this implies that phi classical, the function of t, is little phi e to the I kt. Okay, so what we want to do now is to basically substitute that solution back to the action to get the classical action. Okay, so let me do that here. Yeah.
About the initial secret, the boundary secret,
Sorry?
the boundary secret, initial secret.
Yeah, so this you can also interpret as the no boundary Haru-Hawking boundary condition. Yeah. Yeah, so yeah, if you rotate to complex time direction, imaginary time direction, then basically it's equivalent to saying that there's no boundary.
Only you are talking about the inflation, curiosity inflation.
Sorry, can you ask me?
Talking about only let's say, during the inflation.
So here I'm just computing this object in Minkowski space. It's not we are not in inflation yet, so inflation of course in Minkowski this boundary condition is very natural because it's just a vacuum state. In the past, in inflation there's a choice. This is a choice that we are making. So in general, this in state is not necessarily the Minkowski vacuum. It can be some alpha state as mentioned previously, or some more complex excited states. So this will be just a choice that we will be making when we go to the inflation context, and that choice will be equivalent to the Haru-Hawking no boundary state. Okay. All right, so let's now plug this classical solution back to the action. Now it will be useful to separate this integral. Okay, so time integral, because we are evaluating things at t equals 0, we are only integrating t up to this t equals 0. And, we are integrating over all spatial direction. Now, you can write the kinetic term by integrating by parts. What you get is you first get this phi box phi by integrating the partial derivative. But then because now t has a boundary, there's a total derivative term that you can't neglect. Okay, so on top of that, you will get time derivative of phi dot phi. Okay. So because this is a classical solution that satisfies the equation of motion of box phi equals 0, this term vanishes. And this total derivative just becomes a boundary term. Okay? So this now becomes just the 3x with half time derivative. So here dot denotes the time derivative. Phi classical dot phi classical evaluated equals 0 after taking the derivative. Okay. Okay. Now we obtain the solution in Fourier space. So let's also now go to Fourier space. So when we go to Fourier space, we are Fourier transforming each of these phi's. Okay. So we have d3k, d3k prime with 2 pi cube downstairs. We have half phi classical k at t time derivative. Sorry, there should be no time derivative here because the total derivative just becomes a boundary term at t equals 0. Okay, and phi classical at k prime at t evaluated at t equals 0. Now these d3x. When we Fourier transform, we also get this exponential factors. And this, the purpose of this is just to impose the momentum conservation. It should be, my convention should be 2 pi cubed as well. Okay. So now this phi classical is given by just the exponential plane wave, e to the IKT. So when you take the derivative, it will pull down a factor of IK, right? So this now becomes so I'm now also going to impose the delta function. So k prime becomes minus k, and removing this k prime integral. And now we will just have this when you evaluate everything. Because after taking the derivative, that pulls down a factor of ik. Now you're evaluating things at t equals 0, so exponential plane wave just becomes 1. Okay, and then we are just left with its vectors of phi. Okay, so this is the result for the classical action. So we are almost done. Sorry. Yeah, because you're now taking the time derivative that pulls down a factor of ik, but phi doesn't depend on time. It's just a spatial profile. Okay, so you just get a product of this, and then the e to the IKT goes away when you take t equals 0. Okay, so finally, if you want to compute the 2-point function, you have to integrate over psi squared. When you do that, so you're first taking e to the I action. Okay, so I when you take e to the I action, I squared becomes minus k over 2. And then when you square it, k over 2 becomes k. So what you get is e to the minus integral just k. Okay. Now you can do the Gaussian integral to get the final answer for this. Okay, so when you do this Gaussian integral with some appropriate normalization, you will get 1 over twice k from this. Okay. So that's it's consistent with the expected form for the answer. Okay. Any question about this 2-point calculation? Okay. If not, we're going to move on to the interesting part of the calculation by adding interactions. Okay, so let's now add some interactions. Okay, so now our action will contain some interaction terms. So we're still working Minkowski space. So we have this usual measure, the kinetic term, and then we'll add some interaction Lagrangian. Now the equation of motion, when you take the functional derivative of the action, will now have extra source term. Okay, that corresponds to the functional derivative of the interaction action. Okay, so this right-hand side now has a source term. So for general interactions, of course, we can't exactly solve these equations. What we do is to solve this equation perturbatively. Okay, so to do that, we will perturbatively expand the solution. Okay, so now C classical, we will expand around some background solution in this manner, where by phi bar, I mean the solution that we obtain in the free theory, okay, without any interaction. Okay, so this is phi e to the ikt we just solved. And then we will add some, we will solve this equation perpetually, where now this delta phi would be the solution, formal solution to this with the Green's function. Okay. Okay, so you can solve this equation formally with the Green's function, where g is the Green's function. Okay, and Green's function will satisfy this equation. All right. So let's now solve this equation for the Green's function. We can solve it in the usual manner, but now we have to be slightly careful about imposing the correct boundary condition. Okay. So the boundary condition, remember, is that the phi classical should be 0 when we go to the far past with the I epsilon prescription, and it should reduce to little phi k when we go to t equals 0 time surface. Now it turns out that because we are keeping this solution that we had before that already has the correct boundary term, that means that this delta phi should also should now be 0 when we go to this late time t equals 0, because the previous solution already satisfied the correct boundary condition. Okay, so we can't have any extra term from this delta phi, and that implies the boundary condition for the Green's function. So now when you solve this, now we are going to go to Fourier space again. And then the boundary condition that we are imposing for the Green's function is that when we take one of the t's to 0, it should vanish. Okay? And similarly, the boundary condition when we take this to minus infinity, it should also become 0. Yeah, so we want to, so this boundary condition is really for a phi classical. And we need this boundary condition for the full classical solution to get the correct wave function with the boundary condition. Now we are splitting this full classical solution into pieces, like phi bar, delta phi. But because a phi bar already has the correct boundary condition, you can't have any extra contribution from delta phi. Oh, Green's function, yeah. So yeah, if you have the that boundary condition for the Green's function, then delta phi will satisfy. Okay. All right, so let me keep this. Okay, so when you solve for the Green's function with the boundary condition, then you get the following expression. So let me write down the expression and then explain the various terms. So you get three different terms that contribute to the Green's function, which are given by this. Okay, so product of the plane waves with the theta function, and one with the opposite sign. And then you get an extra term, which looks like this without theta function. So here, the two terms that contain the data function are actually what we have for the usual Feynman propagator, just expressed in this time representation. Okay, so if you go to energy space, then this will be the usual Feynman propagator with 1 over k squared plus I epsilon. Now we have an extra term in the Green's function due to the boundary condition that we are imposing at t equals 0. Okay, so this is an extra term you get for the Green's function when we are computing the wave function. Okay, and then I'll leave it as an exercise that the Green's function that I wrote down over there does satisfy the boundary condition over there. Okay. So with these ingredients, you can now compute the wave function with any interactions. And the rule, the prescription for computing the wave function can be nicely packaged in terms of some set of Feynman rules. Okay, so let me state what these Feynman rules are. Okay, so when you have a diagram, say that looks like this. Okay, so let's consider a very simple interaction, lambda phi cubed. So what you will have to do is to consider. Okay, so maybe let me also write down this diagram. The full point function coming from this interaction. So it turns out that there are going to be two different types of propagator. Okay, one, the propagator that we just derived here is the so-called bulk to bulk propagator, which connects these two interaction vertices for finite time. Okay, so this is the propagator that we're using for the internal lines. For the external lines, we are basically using the free solution that we obtained before with this e to the IKT. Okay, so that will take us through these external lines. So we have two sets of ingredients. So there's a propagator called the bulk to boundary propagator that we use for the external lines. And this is just given by e to the IKT. And the bulk propagator takes this form. Okay. So with these ingredients, let's try to do our first computation of the wave function. Okay. So let's actually compute this object. So what we do is that we basically take the product of this external propagator and then integrate over time from -infinity to 0. And we take the product of 3 propagator with 3 different momenta. Okay, so I'm associating these external lines with 3 different momenta, K1, K2, K3. And if you want to compute this contact 3-point function, you just take the product of this bulk to boundary propagator and then integrate over time. And then you can have some I lambda as the overall prefactor. Okay, so this product of plane waves will turn into this form. Okay, it's just the product of plane waves. So the exponents combine in this simple way. And this is an integral you can do by hand. So when you do this, you bring down this factor of I times sum of k's in the denominator, and factors of I cancel. So what you get is this result, because the plane wave when you evaluate at t equals 0 vanishes, and in the far past limit with the I epsilon prescription it becomes 0. Okay? So this is the answer for this 3-point wave function.
You maximize it when k1 equal k2 equal k3, as you mentioned yesterday.
Yeah, so this will be, you mean the size of this 3-point function?
Size of the 3-point function.
Yeah, this will have some shape. So this is a function of k1, k2, k3. So in the first lecture, I mentioned that this contact type interaction tend to be maximized at an equilateral triangle configuration, and that's basically because this is a symmetric function of k1, k2, k3. Yeah. Okay. So that was very simple. Let's now do a slightly more complicated example of treatable 4-point function. Okay. So now let's try to compute this object. So let me write down the full expression first. Okay, so because we have two interaction vertices, we're going to have two time integrals, and let's attach 4 different momenta to the external lines, and the internal line will also have some momentum that is given by magnitude of the sum of k1, k2 by spatial momentum conservation. Okay, so what we will have is the following. So we have both the boundary propagator for the legs 1 and 2 with time t, and then we have both the bulk propagator with intermediate momentum ki with t and t prime, and k3 with t prime, k4 with t prime. Okay, so this is the integral that we want to do. Okay, so this is simply k1 plus k2. So this plane wave, and this is simply e k3 plus k4 t prime. So it turns out that you can do this integral by hand, but in the interest of time, let me not go through the derivation, but just explain some steps. Okay, so this bulk-to-bulk green function, because it consists of these 3 different terms, you can split it into 3 terms, and let me sort of diagrammatically label these 3 terms in this way. So when you have a theta function with t minus t prime, because these t's range from minus infinity to 0, this theta function means that this is only non-zero if t prime is smaller than t. Okay, so that means that there's a time flow from t prime to t in this way, and the second term implies that there's a time flow from t to t prime. Okay, so the time flow is in the other way. And then the last term with an opposite sign is the term that is sort of disconnected in this way. So there's no time ordering, so it just becomes factorized into just the product of the 3-point functions. And you see that when the external both boundary propagators combine, then turns out that only the total sum of these momenta enters in the computation. Okay, so it turns out that it actually doesn't matter how many external lines you have that is attached to a single interaction vertex. So let me simplify our lives by just truncating the external lines and then just denoting this by these graphs like this. Going the other way, and the last time, let me denote it by dashed line like this. Okay, so I'll leave you to do this computation, and let me write down the final answer for psi 4, which is this object. It's given by 1 over k12 plus k4, k34, k12 plus ki, k34 plus ki. Okay, so this is an exercise. Now, I'd like to mention some important properties of this final result. Okay, so first of all, I'm going to rewrite this. So here I've defined this k12. So kij is ki plus kj. It's just a sum. Now let me write this in a slightly more intuitive way. In this way, where E, so these were variables that denote the energies associated with these vertices. Okay, so this case you can kind of think of energies because these K's are defined to be the magnitude of the spatial momentum. So if we were doing the amplitude calculation, this would be the energy components of the full vector. Okay, so even though in cosmological setting the energies are not actually conserved, so we're gonna just use a language where the magnitude of the momentum we will refer to as energies. Okay, so the first vector, because it's just the sum of k1, k2, k3, k4, this, let me call this total energy. Okay, and these two factors, because these involve energies that flow to each of these vertices, okay, that are partial component of the full Feynman graph. Let me call these two factors as partial energy. Okay. So if you look at this function, it turns out that this wave function has simple poles when these energy factors go to 0, right? So what is the interpretation of this pole? And in fact, this observation turns out to be fully general. Okay, so it turns out that any endpoint wave function has singularities when the total and partial energies goes to 0. Okay, so in physics, whenever we encounter singularity, we want to actually go to this location of these poles and then see what happens. Okay, so what we want to do is to go to the singularities and look at the residues of the singularity and see whether we can identify the residues as in terms of some physical objects. So let's first do that for the total energy. Now, when you do this, when you take this residue, we'll go to this e equal to 0, take e equal to 0. So this limit is the limit where k12 is equal to minus k34, right? E was defined to be k12 plus k4. So this is a limit where we're taking k12 to be minus k34. Now, another remark that I want to make is that this limit is actually not achievable for physical configurations because these magnitudes of these case of magnitudes of spatial momentum that has to be positive for physical processes. So these sort of singularities you can only reach by certain analytic continuation of these energy variables. But we like complexifying momenta. So this is what we also are doing here. Now, when you do this, we get this 1 over E times 1 over E left times ER, E right. Okay, so here, what happens is that K12 flips sign and becomes K34 for the first vector. And the second vector remain the same. But notice that these two vectors combine into just 1 over the Mandelstam variable. Okay, so the Mandelstam variable, if you define it as K3 plus K4 squared, where we're taking the square with the Minkowski metric, eta mu, then we precisely produce this vector. So it turns out that the residue of this total energy singularity is precisely given by the amplitude in flat space. Okay, and it turns out this is a completely general property. So psi n, when you take e going to 0 limit, produces the amplitude as the residue of this singularity. And there's a very intuitive way to understand this. So the way to understand this is by looking at the time integral representation of psi. Okay. So first of all, think about where this simple pole actually came from the calculation. It came from doing the integral of this form, right? So this multiplied by I is 1 over E. Now, the difference between this calculation and the usual calculation that we do in amplitudes is that instead of the pole in E, we usually get a delta function in E because the total energy has to be conserved due to time transfer symmetry. And in the amplitude calculation, the way this arises is by doing the Fourier transform in the time component by integrating over from minus infinity to plus infinity. Okay? But here in cosmological calculations, we don't quite get the delta function because we are breaking the time transfer symmetry by deciding to evaluate this integral up to some cutoff. But what happens is that when you take E equals 0, there's a singularity. And from the integral, there's a singularity because when you put E equals 0 here, this integral blows up because this is no longer oscillating to suppress the contribution from minus infinity. So actually, this integral blows up due to the infinite contribution comes from the lower limit of the integral. So the integral gets dominated at early times. But at early times, the physics should be the same as the physics, the interaction that happens in flat space for scattering amplitudes, because we are no longer sensitive to the boundary in the future. Okay, so when we take this wave function calculation, now when you evaluate things at E equals 0, then we get dominant contribution just from the interaction that happens in the far past. Okay, and In this limit, we therefore expect to reproduce the dynamics of just the usual scattering in flat space. And intuitively, this is why we get this behavior. Yeah, sort of. Yeah, instead of the Fourier transform, yes, it's more like a Laplace transform. Yeah. Okay. Yes, there was a question. Yeah, I think the order of limits kind of matters here. So I think the fact that we are cutting off the integral here and then doing the integral first and then taking the limit is actually yeah. But you do get because this delta function, if you try to evaluate the equal 0, it's also singular. You get the same sort of singularity when you evaluate it equal 0, but it's just a different types of singularity because you're doing the integral in a different order. Yeah. Yeah, so here I'm just doing the calculation in a fixed background. So yesterday I talked about when you compute curvature perturbation zeta correlation function, you have to consider dynamical metric. But then I also mentioned that you can also do the computation by going to the other gauge where you set curvature perturbation to 0 and then just think about the problem as a quantum field theory of some scalar field living in some fixed background. So this is an even simpler problem where we are just doing like a flat space, fixed flat space calculation of some scalar field. Yeah. Yeah. Yeah, so very good question. So far we've done calculation in flat space where we have this just a simple point in E. But it turns out that when you do the calculation in de Sitter, you get some extra. You may get some extra factors of t in the integral that will lead to some high order poles. But the argument is the same. That the leading singular behavior is given by the amplitude. But there could be some subleading corrections as well. So if this is e to the n, there could be e to the n-1 and so on. These terms don't really have a nice interpretation in terms of just a purely flat space object like amplitudes. Yeah, so you can fix this. You can fix this order of the singularity by looking at the actual interactions that contribute to the wave function. So if you have a higher derivative like interactions, then you get higher powers of E downstairs. And there's also like intuitive way to understand this because this E going to 0 is like going to very high energy limit because we are going to very far past. So energy fluctuation wavelength is super short, so we are going to very high energy regime. So if you have like higher derivative coupling like this, then they will give like a higher order pole in the E total. So they will dominate in this E going to 0 limit. So it depends on the nature of the interactions. Yeah.
You're saying that, say, if you consider a fixed de Sitter background, that you still get the same behavior, but with some different powers.
Yeah.
What do you mean by the amplitude in that case? Because
the amplitude it will be the same. It will be the amplitude with the. So you can think about. Suppose you have this diagram, your computing diagram. You can compute it either in flat space or in de Sitter with the same interaction. Say by Q. Then in this E total going to 0 limit, you might get some different power of the E total, depending on whether you're computing in flat space or in de Sitter. but that the amplitude that you get is the same, which is basically the same amplitude with the phi cube interaction. Flat space amplitude. Yeah. The bulk-to-bulk propagator are different, and also the bulk-to-boundary propagator are different. But when you take this equal to zero limit, what you're getting is that you're just picking up this leading term that dominates the integral with some certain powers of t. Okay, so the nature of the bulk-to-boundary propagator doesn't really matter in this particular limit. The only thing that differs is this overall power. Okay. Let me mention it in the next lecture as well. So I guess I'm minus 5 minutes to the end. So let me just make a quick comment, and then we'll continue tomorrow. So it turns out that these type of relation between wave function and scattering amplitudes, there are a lot of these kind of connection between amplitude properties and wave function properties. So because of this relation, you can think of the wave function as some sort of a generalized object of the amplitude in a very precise way. Okay, so because of this somewhat remarkable relation, you expect a lot of the tools and techniques that we have been studying for amplitude may have some natural generalization when we go to cosmology and look at the wave function. So tomorrow's lecture, we will try to use these tools that we use to study scattering amplitudes to do more non-trivial calculations for the wave function. Okay. All right, I'll stop here.
Okay, so far you take into delta phi only up to delta phi. How about the second order, delta phi square?
Delta phi. Yeah. So
include that
right.
Yeah.
So before I was solving this quantitatively by writing phi classical as phi bar plus delta phi. Of course, they're going to be high order.
Yeah. Okay. In that case, what happens?
But all of those high order terms are nicely repackaged in terms of Feynman rules. So these high order terms might contribute to high order endpoint wave function or some loop diagram, but you can get all of those with the same set of Feynman rules.
How about you have the so far Minkowski's signature? That's I think real time or the imaginary time. It doesn't matter on your formalisms. Yes, we could start with the Minkowski signature.
Yeah.
And then there's a real time, and then what happens? It doesn't matter on the real time and the imaginary time or the Euclidean time.
Right, I'm not sure what you mean by.
Usually we have the start with the Hartle-Harking, 1978 and 1979. That's start with the Euclidean time, right? And in that case, what happens?
Yeah, you're imposing essentially the same boundary condition in the far past. So if you go to de Sitter, you can solve for the equation motion of some scalar field in de Sitter, and you find that there's a linear combination of the solutions, and then you can set one of the terms to 0 by imposing the same boundary condition, where when you go to the far past, you're going to slide the imaginary direction by imposing this I epsilon prescription.
Okay. There's no problem. Gravitational path that we can apply, and
so here I'm not considering dynamic of gravity, and in the path integral, when I define the wave function of the even though I call it wave function of the universe, I'm not really integrating over the background metric.
Okay. So, thanks a lot.
So it's yeah.
More question? If not, let's thank speaker again. So. As I mentioned that at 6:30 we'll have a banquet in atrium. Maybe you have a